In this video, we're going to begin our study of interference and diffraction. Interference and diffraction occur when light goes through small openings. And just to give you a little bit of a beginning reference here, when we're talking about interference, interference occurs when light travels through two or more openings, or what we call slits, narrow openings. Diffraction, on the other hand, occurs for one or more slits. So if we put light through multiple small openings, we're going to get both interference and diffraction. In this video, we're going to start to talk about interference. Before we can talk about interference and diffraction, we have to talk a little bit more about some properties of light. Let's talk about what it means to say that light is coherent. So coherence refers to a constant phase relationship between the peaks of the waves coming from our light source. In order to understand why this is important, the first thing we want to look at is a source of light that's not coherent. So if we have a standard old-fashioned light bulb with a metal filament in it, the light coming from that filament is not coherent, and it's pretty easy to understand why. In other words, we know that the way that a light wave is created is by vibrating electric charges, and you can imagine that there's an electron, let's say in this part of the filament, that's oscillating back and forth because it's hot from the current going through it. But an electron at some other point in the filament may be oscillating in a different direction with a different frequency and certainly not coordinated in any way with the first electron. So the waves that come off of our standard incandescent light bulb, they're actually multiple frequencies, and they're definitely incoherent, meaning that the peaks are not occurring at the same time for the light that's coming off. So let's look at an example of a light source that produces coherent light. The best example of a light source that produces coherent light is a laser. And so you'll notice that here, kind of picture the laser beam that's coming out of this laser. And if I look at any point anywhere across the beam, what I see is that the waves are coherent. In other words, if it's a peak here, it's a peak here as well. If it's a trough here, it's a trough here as well. So the light is coherent. The other important thing about laser light is it's also monochromatic. It's a single frequency and wavelength. And that's why when you look at a laser, it will look like just a specific color. So unlike an incandescent light bulb, which is putting out incoherent light across all of the visible part of the spectrum, a laser light is putting out coherent light at just one particular frequency and wavelength. So why do we care about this idea of coherence and whether the light is monochromatic or not? It turns out that if we want to see the effects of interference and diffraction that we're going to be talking about in this chapter, the light needs to be coherent and monochromatic. So we need just one color and coherence. That's why you'll see when we look at interference and diffraction in the lab, we use the helium neon lasers to investigate it because we need that source of monochromatic coherent light. Now, before we can look at interference for light, I want to remind you what we've already talked about in terms of interference. We looked at the idea of what happens when two waves pass on a string. So if I've got two crests heading towards each other, when they cross, we get constructive interference. In other words, the string just shows the sum of those waves traveling on the string. Now again, it's not a permanent effect. It's just a momentary constructive interference as the waves pass through each other, and then they continue to pass in either direction, unaffected from that interaction. We also talked about destructive interference. If I have a peak and a trough going towards each other, the instant that they cross, the string will have a displacement of 0. Those two waves destructively interfere or cancel out. But once they pass through each other, they just continue along like they did before. So when we looked at interference at first with just waves passing on a string, we saw it was a momentary kind of thing that occurred. But then we talked about what happens when you have a continuous sine wave traveling in one direction interfering with a continuous sine wave traveling in the other direction. And remember, that's how we produce a standing wave. Now, what's interesting about a standing wave is that now we have places that are always experiencing destructive interference. And of course, that's what we mean by the nodes. And then we have the antinodes where we're always getting constructive interference. So that instead of this being a passing thing, like just looking at two pulses passing each other on a string, we now get continuous constructive or destructive interference. Well, what we want to look at is, do we see similar behavior with light? And you can probably guess to that, the answer to that question is yes. And that's really what we're going to be talking about. So the idea of the interference of waves actually came out of an experiment that was done by Thomas Young back around 1801. And at this time, the question that Young was trying to answer is, what is the nature of light? Is light made up of particles, or is light a wave phenomenon? So that was a hotly debated topic at that time in physics. And here was the experiment that Young came up with. He said, if I take two narrow slits, so I've got S1 and S2, my two narrow slits, and I illuminate them with the sun's rays. Now, by the way, there's a lot of detail to this experiment. He had to put the sun's light through colored filters. He had to put it through a narrow opening to get a source of monochromatic coherent light. That was much harder for him. It's easy for us. We just turn on a laser. But lasers were only invented around 1960. So obviously Young didn't have those available to him. So here's what Young thought. If light is a particle, then when a particle hits the mask there, it's just going to be stopped. And if a particle goes through the slit, it should just go straight and hit the screen. So the particle theory of light would predict that you would just get two bright lines on the viewing screen for the particles that got through the slits. But in fact, what Young found when he did the experiment is he got a whole bunch of bright lines. And you can imagine that that was quite a confusing result unless you understood the concept of waves that we're going to talk about. So this shows that light behaves like a wave, because what we're getting is a complex interference pattern as the waves go through those two openings. So let's look at, how do we describe or understand that pattern of alternating bright and dark lines? Here's kind of a top view of Young's experiment. So again, he had to take the sunlight, he put it through a narrow opening and through a colored filter, so we had a pretty good approximation of coherent monochromatic light. He then used that to illuminate two openings. Okay, so there's the top view of our two openings. And if we think about what happens in each of those openings, we just get a spherical wave being produced. That's actually diffraction, which we're going to talk about later on in the next video. But anyway, each slit produces a spherical wave. And now what we want to think about is wherever we have a crest crossing a crest, and notice the red here illustrates a crest and the yellow a trough. Anywhere we have red crossing red or yellow crossing yellow, along that line, we're going to get constructive interference. In other words, the waves coming from the two slits are going to add. And so when that wave gets to the screen, we get a bright line. However, you'll notice that along this line, we have red crossing yellow. So we have crests and troughs always crossing with each other. And therefore, no light is going to get to this point on the screen. You move over a little bit more, we see once again we get yellow crossing yellow, red crossing red, so we get a bright line, and that pattern continues. And so if we understand light to be a wave, then we can see that if we have two spherical waves coming out of these two slits, we are going to get exactly the pattern that Young predicted. What we now want to do is figure out what is the formula for describing this pattern. And in order to do that, we've got to understand a few things first. So again, here is a top view of our experiment. And here are the two openings, those two narrow slits that we're putting our light through. So we're illuminating the slits from here. And this is the screen where we're going to see our pattern. Now, one of the things that I've written here is that L is much greater than D. So in other words, the separation between the slits is very small, and the distance to the screen might be a few meters. So because L is much, much greater than D, we can think of R1 and R2 as being essentially parallel, right? So, in a much more accurate scale, these slits are so close together that the lines are virtually right next to each other. Okay, so now what we want to figure out is what is the path length difference between light that goes through the first slit and light that goes through the second slit when they arrive at this point on the screen. And to do that, we have an enlargement of this part of the diagram right here. You'll notice that this distance here is the path length difference, how much longer R2 is than R1. And you'll notice that we can get a relationship for that by just looking at a triangle. So here is the hypotenuse of the triangle, which is D. And notice that this side is what we're interested in. And if this angle is theta, then this angle is also theta, just by looking at the geometry of the problem. And therefore, the opposite side of the angle theta is that side, and that's what we're looking for. And therefore, the path length difference is d sine theta. So why is that useful to us? Well, here's what I've got to understand. If I want to get constructive interference right here, I need a crest to arrive from each slit at the same time. Now, right here in the middle, it's obvious we're always going to get a bright spot because the path length difference is 0, and therefore if a crest is coming through the slit here, a crest is coming through the slit there at the same time, and therefore they're definitely both going to get there at the same time. However, if the path length difference is something else, then if we want to get constructive interference, what we have to make sure of is that it's an integral number of wavelengths different. So in other words, when a crest goes through the slit and a crest goes through this slit, it may not be the same crest that went through, but as long as it's some integral number of wavelengths, then we're going to still get constructive interference. In other words, we'll still get two crests arriving at that point at the same time. And so this is our formula for constructive interference. You'll notice m equals 0 is just that central bright line. M equals 1 would be the first bright line on either side out. M equals 2, the next bright line, etc. If we want to get destructive interference, what we want to make sure of is that when a crest arrives from one slit, a trough arrives from the other slit. And therefore, we need them to the path length difference to be half a wavelength off. And so obviously we can get a dark area here, 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 etc. And so that first dark area would be m equals 0, where when that's 0, it's just 1/2 a wavelength different. 1 would be the next one, etc. So we've got two formulas, one to figure out where we would get the dark spots on the screen, and where we would get the light spots. So let's look at a summary of what we just talked about. You'll notice, by the way, that in my picture here, we don't see bright lines, we see just bright dots. And that's because when we actually do this nowadays, we don't illuminate the full length of the slits. Instead, we use a laser beam to illuminate the slits, and therefore we're illuminating the slits with a dot, and so we get multiple dots on the screen as opposed to lines. Okay, so that's one difference with Young's experiment. So that central bright spot, that again corresponds to m equals 0 in the constructive interference formula. The next bright spot out would be m equals 1. Next bright spot out would be m equals 2, and of course it's on either side of the maximum. Now this is the formula that students always screw up on exams. The first dark spot out from the center, out from the central bright spot, is m equals 0. So if I say find the angle to the third dark spot, notice the third dark spot would be m equals 2 in the formula. Whereas if I said find the third bright spot from the center, that would be m equals 3. Okay, so I'm going to put some stars on this slide. This is really important to get that concept. This diagram, by the way, is just showing you another way to look at this. This is plotting the intensity of the dots, and it's simply telling you that that central dot is the brightest, and then they fade somewhat in intensity as you go out on either side. Let's look at some other vocabulary just to be aware of. The bright spots are often referred to as fringes. That's historical. Remember that when Young did the experiment, he saw bright lines. And you'll notice those lines kind of look like the fringes, like on this nice leather coat there. And so that's why they're called fringes. M is referred to as the order. So m equals 2 would be the second order. We use the word maximum to refer to bright spots, or minimum to refer to the dark spots. So here's an example. The second order fringe or second order maximum would refer to the bright spot where m equals 2. Let's try out a problem using the constructive interference formula. Two slits separated by a distance of 0.1 millimeters are placed 1.2 meters from a viewing screen. Light with a wavelength of 500 nanometers falls on the slits. At what angle will the second order maximum be found? So let's first just kind of draw a picture of it. Here are my two slits. So they're separated a distance d apart, and I'm illuminating the slits with light in this direction. So the light's coming through the slits. And then at some distance away, I have a screen. And we usually use L to represent that distance. So 1.2 meters away is where the screen is. And what I'm trying to find here is what is the angle to the second order maximum. So we know that we're going to get, if we illuminate this with a red laser, we would get a central dot on the screen, and then we would get dots going out on either side. So those are the bright spots that we're talking about. Here, we're asked to find the angle to the second order maximum. So that means m equals 2, and we're using the constructive interference formula. If it had said the second order minimum, then we'd be using the other formula. Okay, so I want to use d sine theta is equal to m lambda. In this case, we'll just go ahead and solve for theta. We can see that theta is the inverse sine of m lambda over d. And therefore, theta is the inverse sine of m, which has a value of 2. Our wavelength is 500 nanometers. We've got to make sure to put that into meters. So 500 times 10 to the negative 9th meters. And divide by the distance d, which also has to be in meters. 0.100 times 10 to the negative third. The key thing is that we know we can't, when we take the inverse sine, we can't have any units in there. And so the key thing is lambda and d both have to be in the same units. I find it's easier just to always convert them both to meters. If you go ahead and calculate this, again, make sure your calculator is in degree mode. We actually want a degree answer. You should get 0.573 degrees. So that would be our answer. You'll notice that that angle is quite small. The dots are going to be very close together on the screen. Let's continue with the problem and answer this. How far from the central maximum will the second order maximum be found on the screen? So we just found the angle to that second bright spot. So we just found theta. And by the way, obviously it's symmetrical, so we could be talking about this bright spot where m equals 2 or this bright spot where m equals 2. And what we're being asked to find is the distance y from that central bright spot. By the way, that central bright spot is often referred to as the central maximum. It's also sometimes referred to as the 0th order, because that's where m is equal to 0. Okay, so we want to find that distance y. And again, it doesn't matter whether we're talking about that distance y or this distance, since they're the same. In order to do this, you'll notice it's just a trig problem. In other words, we know that the length of that side of the triangle is the distance to the screen, L. We've got theta, and we want to find y. So we can see that we're looking for tan theta is equal to y over L, or y is equal to L tan theta. In this case, then, we can plug in the fact that the screen is 1.2 meters away, and the angle that we found on the previous slide was 0.573 degrees, and therefore I get an answer of 0.012 meters. So that would be the distance from that central bright spot to the second bright spot. Let's look at something that hopefully you remember from trigonometry, which is the small angle approximation. Basically what the small angle approximation says is if we're looking at this triangle where here's our angle theta, the opposite side is y, and the adjacent side is L, that as long as L is much, much bigger than y, sine theta and tan theta are basically the same. Now, in order to see that that makes sense, think about a triangle where I try to draw it so it actually meets this condition. What we're saying then is that our height y, or our side y, is very small compared to L. Well, here's what the hypotenuse of that triangle looks like. So there's our angle theta. Notice that basically the hypotenuse and the adjacent side are effectively the same length. Obviously the hypotenuse is slightly greater, but you can see whether we do y over L or y over the hypotenuse, we basically are going to get the same value. Just to try this out, if you take the sine of 5 degrees on your calculator, so that's a pretty small angle, we get 0.0872. If you take the tangent of 5 degrees, you get 0.0875. So you can see that they are very close. And so as long as you're less than 5 or 10 degrees, this is a good approximation. The reason that this is useful is that our formula for both constructive and destructive interference for the bright and the dark spots, they both contain sine theta in them. So let's say in a problem you're given y and L. Instead of first having to find theta, what you can do instead is simply replace sine theta with d, or replace sine theta with y over L. And it just saves you a step in problem solving. Let's look at an example that will allow us to apply the small angle approximation. The second minimum occurs on a screen 9 millimeters away from the central maximum. The distance from the double slit to the screen is 1.2 meters and the slit spacing is 0.1 millimeter. What is the wavelength of the light being used? So a couple things here. First of all, notice that we're looking for a minimum, so we need the formula with the 1/2 in it for destructive interference. And then also, we've got to make sure we get the correct value of m. Remember that for this formula, the first dark spot on either side of the central bright spot, that's m equals 0. So the second dark spot is m equals 1, and that's what we're looking for. So that's the most common mistake students make on exams, is not getting that m value correct. So in this case, we can see that m is equal to 1. Okay, so now what we've been given then is this distance y. That's the 9 millimeters. We've been given the slit separation d, and we've been given the distance to the screen. So in this case, I'm going to use the small angle approximation. Again, I could just use inverse tangent and find theta, but I'm going to save myself a step. So my formula, d sine theta equals m plus 1/2 times lambda, I'm going to rewrite that where I'm going to substitute the fact that sine theta is approximately equal to tan theta, and since tan theta is exactly equal to y over L, I can substitute in y over L for sine theta. And now I just need to solve that for lambda. Lambda is going to be d times y over L times m plus 1/2. And at this point, I'm just going to go ahead and plug in those values. So lambda is equal to d, that's the slit separation, and that's 0.1 millimeters. So I've got 0.1 times 10 to the negative third. I'm putting everything in meters. Y is just the distance to the, y is the distance to the dark spot. That's the 9. So I've got 9 times 10 to the negative 3. And then I'm dividing that by L, which is 1.2, and m plus 1/2. We figured out that m is 1, so that's 1.5 or 3/2. And if you calculate that, you should end up with a wavelength of 5 times 10 to the negative 7th meters. By the way, I'll just make a note that that's 500 nanometers. Just a little hint. Earlier in the course, we said that visible light has a range of 400 to 700 nanometers. That's a useful thing to remember, because in a problem like this, if you're solving for the wavelength, if you don't get a value in that range, you've probably done the problem wrong. Okay? So if it's a visible light problem, our wavelength has to be in the visible part of the spectrum. Okay, that's it for this video. In our next video, we'll look at diffraction.